Welcome everyone to OneQuantum Africa weekly meetings. It's really a pleasure to have you guys on. I know that it's usually a busy day, but all the same, I appreciate those who could make it. It's really a pleasure to have you on. As you know, today we actually have Amiri Karamlu from MIT. He's going to share with us his work in research at MIT in quantum simulation using superconducting quantum processors. He is a researcher in the engineering quantum systems group at MIT. So let me pay the bills and just share with you a bit about OneQuantum Africa. So why do we need to talk about quantum in Africa? I think generally, to me, quantum is important for Africa because it has been giving us some great technologies over the years. And because of the fact that we are continuously understanding it and getting to know a lot of things about it and getting deeper into the physics, we are now able to introduce some new technologies that will create new business opportunities and help us to solve some of the challenging problems in the world. And it is important that Africa and its people are equipped with the skills and education that will enable them to contribute to this technology and also shape it as it evolves, since it is going to affect a lot of the enterprises that we know today, bring on new enterprises, create future careers, and build future workforces as well. So it is important that we pay attention, that we contribute, that we hear what experts are looking at, that for the experts that are based in Africa, we also get to know them, we showcase their work, we celebrate our own heroes, and we also connect with the global community and keep in touch with developments in the quantum tech space. Let me tell you briefly about OneQuantum. OneQuantum is a global community which is built on a foundation. We believe that it is very important to build strong local communities. And in these strong local communities, we are going to be able to influence the growth of quantum in these local communities, but we want to give people in these local communities an opportunity to also connect with the global community so that we can build an industry which allows everyone to be successful, which is fair, and which is profitable. So you can see from this slide that we also offer mentoring. We've got a career space where we receive CVs from people around the world who are interested in a career in quantum, so that employers can get to have access to these CVs, and it gives everyone an opportunity to be considered for most of these jobs. And because we know that people need the skills and the education to develop capabilities that are required by the employers, we've got mentoring, and we've got work on that continue to develop people's skills and to equip people with education as well in the quantum tech space. We are going to host Africa Quantum Summit, or a Quantum in Africa Summit, from the May 12th to the 14th. The 14th because I think the time zone there also caters for people in Australia and other countries. So it's actually May 12 to 13 if you are in the same time zone as I am, which is SAST. And we want to showcase quantum experts in the continent. We want to bring some experts from across the globe to unpack what we think are low-hanging fruits in quantum in the continent. And we are going to share details about this as we go, as those things come into place. We are at the moment busy putting together everything else that is required and that is a successful event. But in the meantime, you can share this opportunity with your friends and colleagues. You can sign up and you can reserve your spot, and we are going to share details as we go, like I said. If you've got any other ideas and you are interested in participating, or you want to suggest a speaker, you can let me know at my email address. I think I've shared it in the newsletter. I'm also going to share it as the meeting proceeds. Let me also take this opportunity to talk about the Women in Quantum Free Mandarin program, which was launched recently. So we partnered with Keysight Technologies, or Women in Quantum rather partnered with Keysight Technologies, but this has been made available to all the communities or all the chapters of OneQuantum, including our community in Africa. So don't hesitate to submit your application if you're interested in mentorship. It's really a beautiful opportunity to develop your capabilities in quantum and to refine them and to further your personal development endeavors as well. So I encourage you to apply, and it's not only for women in quantum, it is for every community member of OneQuantum. So feel free to submit your application. I think the email address is brook@onequantum.org. I'm going to share that as well in the chat as we go. Let me also tell you about our new chapter in Nepal, which is being run by Manish Thapa. They are hosting a webinar, let's call it, on building a quantum computer with superconducting qubits. It's happening tomorrow, Thursday, at 3:15 p.m. SAST. So make sure you sign up and reserve your spot for that one. You are free, you are free to attend, and it will be something great for those that are interested in learning about quantum hardware. You can keep in touch with me. Let's keep the conversation going on the following handles: Twitter, LinkedIn, Facebook, GitHub, and website. I'm going to be responding to the chats. Don't worry, as soon as I'm done and I've handed over to Amiri to take this presentation forward. Let me also talk about today's speaker. So thank you very much, Amiri, for joining us. We're really pleased you could find time to be with us today. Amiri graduated from MIT with a BSc in Physics and Electrical Engineering and Computer Science. And he also has got a Master's in Engineering, Electrical Engineering and Computer Science, which he got in 2018. His research motivation is to use quantum mechanics to gain an advantage over current technology and protocols. As an undergraduate, he worked with DEC England on control and high fidelity readout of NV centers in Diamond. I love NV centers in Diamond, and it was my first time to actually learn that we can use Diamond for something else other than jewelry. So it's really been great, and shout out to you, Amiri, on that work. I've worked on that, so I just thought I could highlight it. I'm so excited to hear about NV centers every other time I see them. I see them getting mentioned. So you will talk about quantum simulation using superconducting quantum processors, which is really exciting. It's going to give us a solid background on why that is important and the great work that he's doing, and it's really going to be amazing. Next week, we are going to host Florian Frois. He's a research and development collaboration manager at ID Quantic in Geneva, Switzerland. Some of you may know ID Quantic as one of the leading companies in QKD, in quantum random number generators. I think they've partnered with SK Telecom in South Korea, and they are the ones behind the quantum random number generator that is being used in the Samsung 5G phone. I think they are already adding, there's a second Samsung phone that is already going to be carrying a QRNG, which is a quantum random number generator. So it's going to talk to us about QKD, PQC, which is post-quantum cryptography, and quantum random number generators, and put them in context in terms of why should we care, what are these devices used for, what are these techniques used for, why are they important, and when do they apply, when should we think about them. So that's something to look forward to next week. With that, I think I am done, and I'm going to stop sharing my screen and allow Amiri to take over and start sharing his screen and take over this presentation. So thank you very much, Amiri. It's really a pleasure to have you on, and looking forward to your presentation. You can take it away.
No, the pleasure is mine. Thank you so much for the kind introduction and the invitation. My name is Amir Karamlu, and I'm a graduate research fellow at the Engineering Quantum Systems Lab at MIT. Today, I'll be talking about quantum simulation using superconducting quantum processors. However, I will not be talking too much about superconducting qubits. So if you have any questions about that, feel free to ask me on the way. And in general, the format of the talk will be that we'll start with some motivation as to why do we need quantum simulation and what is quantum simulation, and then we'll get more and more technical as we go along. So feel free to stop me at any point. Ask me questions about the technical details, of course, but also ask me more higher level questions if you see fit. Because again, parts of the talk will be technical, and I don't want the beauty of the physics to get lost, or the beauty of the concepts to get lost in technical details. So feel free to stop me and ask me questions at any point. And there could be questions like, what does this thing mean? Like at a high level, what are the implications? So with that, I would like to get started. First, I want to acknowledge my team members, both at MIT Lincoln Laboratories and the Engineering Systems Group. Without them, this work wouldn't have been possible, and we're very lucky to have the team that we do in place. So let's start by motivating quantum simulation. So the idea of quantum simulation was posed by Richard Feynman about 40 years ago, actually, where he stated that nature isn't classical. And if you want to make a simulation of nature, you better make it quantum mechanical. And by golly, it's a wonderful problem because it doesn't look so easy. And I can attest, someone who works on this problem, I can attest that Feynman was right about it not being easy. So Feynman's proposal was, instead of using a classical system to simulate other quantum systems, let's use, some well-controlled quantum system, i.e. a quantum computer, without actually him naming it a quantum computer at that point, to simulate other quantum systems. Well, so classical computing resources required for simulating quantum systems grow exponentially with the system size. For those of you who are well versed in quantum mechanics, you know that with every single particle, let's say a two-level system added to your overall system, the number of probability amplitudes, or rather the number of coefficients that you have to keep track of, doubles. So you can see that by adding an extra particle, your system size, or by adding extra particles or extra qubits or whatever you want to call them, extra electrons, the resources required classically to keep track of all these amplitudes will grow exponentially. Now, there are tricks to work around it, but highly correlated systems seem to be impervious to those tricks. So the overall consensus is that, again, the classical computing resources required for simulating quantum systems is a lot. Well, what are the applications of quantum simulation then? Well, the first application will be in chemistry. There's this process, the process that we use for producing ammonia is this Haber-Bosch, called the Haber-Bosch process, and it consumes around 1% to 2% of the global energy consumption every year. Now, if we could somehow find a way to optimize that process, we would be saving a lot of energy, plus we would have maybe potentially even a process that's more efficient, produces more ammonia for the same amount of original ingredients. Now, this optimization task is hard for classical computers. However, we believe that if we have a quantum computer, we could actually tackle this problem and understand and simulate the dynamics of the molecules that lead to the creation of ammonia. Another application that I can discuss, actually will be the main focus of my talk today, is in condensed matter physics. Now, of course, a reach goal for what we would like to accomplish with a quantum computer is exploring physical phenomena that are not well understood currently, both at the experimental level or rather at the computational level and at the theoretical level. such as exploring high TC conductivity. And high TC superconductivity is just high temperature superconductivity. So today my talk will mostly be focused on simulating condensed matter physics. So with that, interacting many-body quantum systems exhibit rich fundamental physics and can serve as foundation for future quantum computing hardware. So if we have a better understanding of, again, these strongly interacting many-body systems, we might be able to use that knowledge to actually develop better quantum computers, better quantum hardware for the future. However, they are difficult to study analytically and exponentially difficult to simulate with a classical computer. Some of these problems, some of these interacting many-body systems problems have no analytical solutions known yet. So no formula that explains everything with just simple equation. And as I mentioned earlier, since the amount of resources required to keep track of the system classically grows exponentially, they are also very difficult to simulate using a classical computer. However, quantum computers can simulate the dynamics of condensed matter systems efficiently because, again, quantum computers are quantum systems, and therefore the quantum behavior is intrinsic to them. So they don't have to essentially spend extra memory trying to keep track of everything. And something that I will discuss in this talk is that we use the Hamiltonian of these quantum systems to simulate quantum transport and localization. And quantum transport and localization can be used to describe the conductance or the insulating properties of different material. And in order to be able to do that, we need accurate quantum control for each of the sites in our quantum processor that I will discuss today. So there are three types of quantum simulation that I want to talk to you about today. The first one is analog quantum simulation, where we engineer the internal Hamiltonian of our processor to match the Hamiltonian of the system that we're trying to simulate. And then we just let time pass and we see what happens. So a good example of that is simulating a solid crystal, an electron in a periodic potential made by ions. You can think of it as an electron in a crystal or an electron in a metal with this optical lattice system, where we reproduce this periodic potential by optically interfering laser beams. And we essentially, we don't trap necessarily, but we place atoms in this lattice. And based on the behavior of the atoms in this optical lattice, we try to simulate the behavior of, let's say, an electron in a periodic potential in a crystal. So this is the electron is a system in a solid crystal, is a system that we're trying to simulate. And the way that we're doing it in an analog way is to emulate this potential with, again, an optical lattice and seeing how atoms behave in this optical lattice. And this is well controlled. So this was analog simulation. Now, another approach is digital quantum simulation, where we use single and 2 qubit gates for simulating the evolution under a certain Hamiltonian. An example of an algorithm for digital quantum simulation is, and maybe let me pop the chat open on the side just in case there are any questions. An example of a digital quantum simulation algorithm is just a quantum phase estimation circuit that I have here, where we try to estimate the essentially the energy of a certain eigenstate of a unitary time evolution. And finally, the last approach that I want to discuss, and this is something that we use in our work, is analog digital quantum simulation, where we combine single qubit gates and potentially some 2 qubit gates and the time evolution under an engineered internal Hamiltonian. Now, the nice feature for this is that digital quantum simulation is actually very expensive. And although it is our eventual goal to reach there, the quantum resources that it requires are beyond the capabilities of our present day quantum computers. However, if we can combine some features of analog quantum simulation and some easy features like single qubit gates of digital quantum simulation, we actually might be able to do things and do things of note, which we will see in this work. So in the work that I'll be talking to you about, we mostly work with analog quantum simulation and analog digital quantum simulation. The platform that we use for our quantum simulation is superconducting quantum circuits or superconducting qubits. The chip that I'm using for the results that I'm talking to you about today consists of 9 flux tunable transmon qubits, and each one of these, squares or inverted square, or not inverted, just squares is 1 transmon qubit. They have local flux lines which allow for individual site frequency control. So I can set the energy or the frequency of each of the qubits to some desired value individually. And they're 2D connected with nearest neighbor coupling. So here we're in a 2D grid, which will allow us to simulate both 1D and 2D systems. And here the circle that I drew a circle around one of these superconducting qubits so you can see what it looks like. Now, the system is described by a Bose-Hubbard Hamiltonian, and I will describe the Hamiltonian bit by bit. So the Hamiltonian form looks like this. The first term in it is the site energy. So what this tells us is if I have, some number of particles, in this case could be photons, microwave photons for superconducting qubits, but some number of particles on each site, how much energy will my system have based on that? Now, the next term will tell me that if I have more than a single particle on each site, what is the energy penalty that I have to pay to accommodate that? So the idea here is that when particles are on the same site, they interact, and that interaction comes with an energy penalty in a sense. And finally, the last term is a coupling interaction. So what is the interaction of one site with its neighbor? And this is usually in terms of hopping or exchange interaction. Now, in our work, in our system, this U term, the coefficient in front of the on-site interaction, is much larger than the coupling interaction. So we will never populate, or with very low likelihood, will populate the second excited level of a neighboring qubit just based on this exchange interaction if we only have one particle on each side. And this allows us to basically ignore this middle term, this green term, and simulate a tight binding Hamiltonian for a single particle or multiple particles. Now, we first start by investigating quantum random walk, which is just quantum transport. A single excitation, if you put a single excitation or a single particle in a quantum lattice, it will propagate via a quantum random walk. The quantum walker, or the particle that's exhibiting the quantum random walk, exhibits ballistic transport, which means that the distance from the source goes linear in time, as opposed to diffusive, which is when things go as square root of time. So in our case, we can prepare a 1D lattice by taking the circuit that we have. Since we have individual site control on each qubit, we can far detune the qubit frequency of these two sites such that they don't interact with the rest of the lattice. We can place an excitation or a particle on one end and then observe the population of each site at different times. And what we see is that we observe a 1D quantum random walk over a chain of 7 qubits that is in very well agreement with simulation. So here, you can see that the particle wave packet is moving ballistically in time, and then it reflects off of the open boundary that we have, the other end of the lattice. And after that, you see some interference effects here in the in the particle wave packet, and that's just due to, again, interference caused by the boundary. And we can actually extract the speed of the random walker by looking at the second moment of the particle position. Of course, I'm taking the square root here so that things are actually linear in time, but we can see that again, before bouncing off of the other end, before reflecting off of the other end of the lattice, the particle speed is linear, and it matches the square root of 3 times j that I claimed earlier. Now, we can also repeat the similar experiment for a 2D random walker. This time we have all of our lattice qubits on resonance, and we place an excitation on the corner of the lattice. And we observe the same random walk behavior. Now, here's something that's worth noting is that in a 2D lattice, like this 3x3 lattice that I have, the particle will propagate along the diagonal symmetry axis of the lattice, meaning that, the particle starts at this position 0 that I have marked here, and then it will spread into 1, then 2, then 3, then 4. And these are distances away from the source, Manhattan distances away from the source. So the way that I'm showing this quantum random walk in my results is that I'm just taking the particle sum of all the sites that are at a given distance, again 1, 2, 3, 4, or 0 from the propagation source. And again, we see the same ballistic behavior. And in this case, in this lattice, the quantum particle propagates with average speed of 1 plus square root of 3 divided by 2j. And I think what is worth noting here is that in 2D, the particle in a 2D quantum random walk, the particle transport is actually faster than a 1D random walk. And intuitively, that's because of the existence of more paths for the quantum interference to take place in order for the particle to make it from the site that it started at to some other site on the lattice. Next, we can probe the entanglement propagation in the lattice as a result of this random walk. So entanglement propagates among the qubits that are at the same distance from the source. And again, this is due to the symmetry present in the lattice. We use 2-qubit state tomography for probing entanglement. And we use this metric called concurrence, which is a monotonic metric for quantifying entanglement. So the value of concurrence will be 0 if 2 sites are completely separable, they're not entangled at all. And it will be 1 if the 2 sites are maximally entangled, and somewhere in between for any arbitrary amount of entanglement. So with that, we first look at the entanglement between the sites at distance 1 from the source. That's qubits 4 and 8. And we can see that, as the particle propagates through, there's some entanglement created, the value of concurrence goes up, and then things drop down as the particle leaves that distance from the lattice, and we see this revival and decay in a coherent fashion. Next, we can look at the entanglement among the 3 sites, or the pairwise entanglement among the 3 sites at distance 2 from the source. And of course, we have 3 different pairs of qubits here, 1, 5, 1, 9, and 5, 9. And again, we see close agreement in terms of entanglement creation and the following entanglement with what we expect based on simulation. And finally, we look at the entanglement between the qubits at distance 3 from the propagation source. And again, we observe the similar creation and fall of entanglement as a particle is propagating through. So now if I actually plot these all together, I can create a propagation map and an entanglement propagation map. Here at distance 0 and 4, I only have a single qubit. So I'm just plotting the population that is occurred on those qubits at different times. But at distances 1, 2, and 3, I'm plotting the average concurrence, or you can think of it as average entanglement. And you can see that the entanglement propagation in our lattice shows a similar behavior as our quantum random walk, which is to be expected. Now, I want to look at how the quantum information propagates throughout the system that I have. So entanglement, the creation of entanglement is a signature for quantum information propagation. However, there's even a better signature that doesn't depend on these non-local interactions. So for that, I want to give you a bit of a schematic of what's happening. In general, when you place a perturbation on the system at some time, let's say t naught, this is some information in the system. But as your system evolves, the information is disappeared through the non-local degrees of freedom. And this is called information scrambling. So this initial information that you have will spread throughout the lattice, throughout the system that you have. And it's actually very hard to probe it, at later times to actually extract the information. However, something that we could do is that we can actually reverse time, do some backward time evolution, and retrieve the information again by rewinding time. That is something that quantum mechanics allows us. So, we start with the information being completely scrambled, and then if we rewind time, we recover the information. That's called the Loschmidt echo, and I will talk about it in more detail. Now, something that could happen is that in this rewinding process, if there's a perturbation at some time, and the perturbation can be like any butterfly operator, any disturbance to the system. It disturbs the reversibility of the time evolution of this W, which I have here. Now, if this perturbation, there are two scenarios, right? This perturbation could happen outside the light cone of my time evolution, meaning that actually, if I reverse time, I'm not going to feel the effect since my quantum information hadn't reached that far yet. In that case, I can, if I reverse time, I will recover my original quantum information, and this eventual perturbation will not affect it. However, if the perturbation is within the light cone of my quantum evolution, meaning that if I have quantum information reaching to the site that this perturbation happens, then rewinding time will not necessarily recover my initial bit of quantum information. And we can use this operator growth as a way to track quantum information propagation throughout our lattice. So it's just quantified using squared commutator, which is defined as we see here. It's just the expected value of the squared commutator of the perturbation, the time involved perturbation, and the initial operation that we had. And what we call, and then this, you can write this as 2 minus 2 times the real time of this f of t. And this f of t is an out of time ordered correlator. And that's what we use to track quantum information propagation throughout our system. So let's talk about how do we rewind time first. So as you might know, in quantum systems evolve under a certain Hamiltonian, the Hamiltonian the energy equation that describes the system, which in our case has the following form. Again, I said that we have, this is the nearest neighbor interaction, and then this is just some energy on each side. Now, the natural time evolution again is just going to be e to the power of negative I, h, which is a Hamiltonian times t. But now I can also think of this as evolving under another Hamiltonian minus h for some time minus t. So now here's the trick. I can actually get this, minus t or time reversed evolution if I evolve under the Hamiltonian h, or under the Hamiltonian minus h. So how do I invert my Hamiltonian? The goal right now is to get a negative sign in front of what I have here for the Hamiltonian. Well, turns out there's a neat trick actually. So these exchange terms, if I apply a z operation, a sigma z, a Pauli z operation on one of the two, one of the two terms here, it actually leads to a negative in that term. So all I'm doing now, and this is the analog digital part, is that I will apply a sigma z operator to every other qubit that's not a neighbor. And with that, I will manage to inverse or add a negative sign to all the terms here. And now for the second part, the part that has delta omega I divided by 2 times sigma z, I can actually go and manually, or by manually I mean using a pulse sequence in my control, flip these detunings from plus omega I to minus omega I. And that way I'll end up with, and if I let the time evolve for the same amount of time, I end up with e to the negative I, negative ht, which is the same as evolving under the original Hamiltonian, but backwards in time. So again, the goal here is to inverse time evolution, which is called a Loschmidt echo. And we actually try this out. So in our case, we start by preparing an entangled state between qubit 7 and 4 using this sequence, an X gate, a square root of I swap, and a phase gate. Now, if those sound foreign to you, don't worry about it, but this is the entangled state that results. And now we want to see if we can recover this entanglement by rewinding time. So we let the system evolve for some time, and then we use our protocol to reverse time evolution or rewind time, and we want to see if we can actually recover this entanglement. And we see that we can. So here, what I'm plotting in red is the fidelity, the state fidelity between the initial state that we measure and how that changes throughout time. And in the blue, we have the fidelity between the states that we measure and the ideal theoretical state that we think we prepared. Now, this is without doing any span cancellation. So these fidelities aren't perfect. But what we can see is that we're actually maintaining our fidelities pretty well. So we managed to recover the entanglement pretty well for times up to 150 nanoseconds. And just to give you some perspective, 150 nanoseconds is actually a decently long time for our superconducting systems, because that's 10 times the time that it takes for one qubit to swap with its neighbor, roughly. Yeah, so we look at, again, the density matrix of fidelity at 2 times, initially, like when we start, and, at some time of 70 nanoseconds. And we can see that, again, we managed to recover the entanglement pretty well, but we have some leakage at later times, some error at later times, and that's mainly due to extra terms in our Hamiltonian that we're not accounting for, in our system that we're not accounting for. Now, we can use this tool, now that we know how to rewind time, we can use it to probe information propagation with out-of-time order correlators. So to the left here, I have the quantum random walk plotted in 2D, plotted as a reference. And you can see the back and forth motion. And now what we do is that I can actually calculate the OTOC when I have no particles in the system. And of course, the way that we calculate the OTOC is by essentially using this equation that is explained more in the paper that I will reference towards the end. But it just looks at essentially the commutator value. That's the end goal. And what this tells us is that here we see that the quantum information also propagates linear in time or ballistically, and it follows the same trajectory that the quantum random walk does, which is a good sanity check, because the claim that I made earlier is that in our lattice, at least when there are no extra particles present, quantum information propagates with the particle propagation. But now we can add additional particles to our lattice. So, here's what the OTOC looks like, or the quantum information propagation looks like, with one additional particle, with two additional particles, and with three additional particles. And you can see that the features might change at higher times, but the real bit of physics here is that we still see the ballistic propagation of quantum information, or the light cone of the quantum information propagation, in the presence of these additional interactions. Now, let's switch gears and talk about what happens if you have some disorder in our lattice. So normally, if our lattice is completely on resonance and uniform, the particle wave function will be spread equally or evenly among all the sites of the lattice. However, if we add disorder to our lattice, the particle becomes localized onto a certain site, and the probability, you can think of it as a probability, or the particle wave function will decay exponentially away from that site. So now the probability of finding the excitation, like let's say 2 sites over, is much lower, it's exponentially lower. Whereas in this case, the probability of finding the particle on every side would roughly be the same. Now we can track this. So again, we can both track this in 1D and 2D by the way that we probe this in experiment is that we introduce a uniform lattice disorder drawn from a bandwidth of delta. So this delta is the disorder strength, and it tells us essentially how wide are the sites spread out in a sense. And what we see is if I place an excitation on one end, let's say the source, as I increase the disorder strength, the excitation becomes more and more localized on the source. So less and less of the excitation leaves, or there's a higher probability of finding the excitation on the source. Whereas, again, the distance that the particle travels, which I'm depicting using the second moment of position, decreases heavily as we increase the disorder strength. And we see the similar behavior in a 2D lattice. Now, the notable difference is that in 1D, we are way more susceptible to disorder than we are in 2D. So for the same amount of disorder, we see less of a localization effect in 2D versus 1D. And again, that goes back to the existence of many paths in 2D for a particle to get from one point to another. Now, we can actually quantify localization using something called a participation ratio, which effectively tells us, how much of the wave function is on a given site. Now, if the wave function is fully extended, if we're fully delocalized, this participation ratio is going to be equal to n. And if we're fully localized, our participation ratio is going to be equal to 1. So again, in the case that we're fully extended, the wave function is extended over all n being the number of sites, all n sites. Whereas if we're localized, we're like very localized in the participation, then the wave function is only really on a single given site. So in this case, for a given disorder strength, the mean free path of the particle before it scatters and stops was showed as L, and that's just the coupling strength divided by the disorder strength squared. And what we see by plotting this participation ratio for different disorder strengths is that we notice that, of course, it decays as it gets smaller, as the disorder strength gets larger. That intuitively makes sense, because as we increase the disorder, the particle becomes more localized. So we expect the value of the participation ratio to go down, but it also follows the scaling that is predicted from the scaling theory of localization in 1D. And we have a similar observation in 2D. Again, as we increase the lattice disorder, the participation ratio decreases, and it follows the trend that's predicted in theory. Now, how does information propagate in a disordered lattice? So again, we have the same Hamiltonian that we used to describe the system, and now we're introducing a random lattice disorder, which is roughly equivalent to 10, like to delta being equal to 10 J's, or in this case, the second moment, or rather not the second moment, but the standard deviation is 2.7 times J. So when we have a single particle in the system, we're of course, localized, we're Anderson localized. So you can see that, the same way that the excitation doesn't reach all the way to the end of the lattice, that quantum information is also localized. Because again, the quantum information, when you have only a single particle, propagates as with your particle. Now, as we add more particles, we notice that localization is slowly overcome. So in this case, we have one particle, on this one side, where our source is at 7, or we're seeing how the information propagates from 7, and you start seeing that you actually do get some quantum information reaching this distance 4 at a later time, but still there's some information reaching, whereas you didn't have any when you didn't have any particle. When you had 2 particles, you see that this quantum information actually reaches that point even earlier. Now, we repeat this experiment for 12 random realizations of the lattice disorder, and what we notice is that by adding particles to our lattice, our quantum information actually reaches the furthest side faster and faster with the number of particles that we add. So the speed of information propagation in a disordered lattice increases with the number of particles in the lattice. And this suggests that the particle interaction that we have in our system is actually a counterforce to the localization. So localization prevents quantum information from spreading, but the fact that you have interaction between your particles actually assists this particle spread. And this is a possible signature for a phenomenon that's not theoretically well understood and still needs to be experimentally more explored, known as many-body localization. Or rather, how do systems with many particles become localized in 2D or not, in 2 dimensions? So to summarize the work that I've been talking about, we simulated the dynamics of particle transport and localization in 1D and 2D lattices. We probed how entanglement propagates throughout the lattice as a result of a quantum random walk. And then we observed that quantum reversibility or time reversal using a Loschmidt echo. And we studied the propagation of quantum information using out-of-time ordered correlators. And with that, I want to draw your attention to the work that we have, to the preprint that we have published so far on the details of our OTOC experiment, or the quantum information propagation experiment. And we're also going to have another paper out soon, hopefully within the next month, talking about quantum transport and localization in 1D and 2D type binding lattices. So with that, I want to thank you for your time, and I'd be happy to answer any questions.
Okay, thank you very much, Amiri. Really beautiful presentation. I got some appreciation via DM. People were a bit shy. Some of the people were a bit shy to express their their excitement here. Perhaps they were afraid we were going to ask questions. But all the same, thank you very much for a beautiful presentation. So yeah, anyway, we've got the floor open. If you've got any questions, you can come through. I'm going to share a few questions that I received. The people who are following up the meeting, some are a bit busy and they've just been sending me some messages that I think I'll pull out and read as well. Before I do that, I wanted to give people actively attending this meeting to come through. So feel free to ask anything. There are no stupid questions here. We are all here to learn about this field, and we are all still learning. So feel free to come through.
It doesn't have to be limited to the content that I discussed right now, of course. If it's anything peripheral, but saying there are a lot of details that don't fit in a 30-minute, 40-minute presentation. So feel free to ask away, and I'll do my best to answer all your questions.
Okay, that sounds good. Let me be taking a question while we're waiting for that to happen. So one of the questions I got was, so you can do the same simulation using other hardware modalities like ion traps, cold atoms, etc.
Yeah,
And
that's correct. So of course,
how would this be different? Or do you have plans to test this on different modalities in terms of hardware as well?
Yeah, so doing these experiments is actually very difficult, and I'm personally an expert in superconducting qubits, and I know how the other modalities work, but I don't have any experimental experience in using them. So I personally don't plan on implementing my experiments on other modalities. But of course, some of the results that I've discussed have been explored. Some of these physical phenomena have been explored on other systems. Like for example, quantum transport is something that's been studied and simulated on uh, trapped ions. I would like to say optical lattices, superconducting qubits by other groups. Of course, now we're doing it in 1 dimension and 2 dimensions, and we're looking at different properties. But bits and pieces of our work, are these are like phenomena that are of interest to the experimental physics communities around the world. So they have been explored on other platforms. Now, something that I can say as to the advantage of using superconducting qubits is that with superconducting qubits, you have access to these nice, single qubit operations, these nice gates, and good readout. And I think that makes a big difference as to the quality, and also our control is much better than other platforms, and that allows us to have data that's much more accurate than what's been previously reported for Anderson localization, for random walks, and so on and so forth. And of course, since we have, since we can do readout and we can do tomography at the end, we can actually extract information about our quantum system that wouldn't be possible necessarily if you're using, let's say, another platform like optical lattices, where you can count the number of atoms on each side, and that's about it.
Okay, I think I understand. That's great. So you can unmute yourself and come through, if so that I take also questions from the people who are actively attending. But like I said, I'm pulling up some questions that I received as well via different platforms from people who are interested in attending this presentation. So I see that you guys have also done some great work with 3D integration. Is there anything you can say that is related to this work and the 3D integration?
Yes, so the chip that I'm talking about today has a 2D planar design, but of course our future generation chips will be 3D integrated. And the reason for that is if you look at the chip here, let me get the laser pointer. If you look at the chip here, so this is a 2D design, and you can see that it's already pretty full with either qubits or resonators and flux lines. Now, in our next generation chips that are being fabricated right now as we speak, we're planning on looking at larger lattices, so 4x4, 5x5 instead of 3x3. But also we're adding tunable couplers and these additional features. And with a 2D planar design, it's almost impossible to route all the lines required for that. So the chips that are being fabricated right now are both 3D, are done using 3D integration and also using TSV.
Okay, that's great. And when you look at simulation, are there any benchmarks? For example, this question was, how do we trust results from simulation? Is there any benchmark that people use or that is industry standard? What are your comments on that?
Yeah, so I guess so all the results that I've discussed today are ran on at most 9 qubits, and those are we can simulate them not easily, but they're definitely doable on a normal computer. like some of the OTOC simulations that I showed, took us around like 3 days running on an AWS server to complete. But these, we can still verify our simulation results and outcomes using Q-tip simulations or some other simulation methods. So we're still in the regime that we can verify things, but of course, as our system gets larger, as we go to 16 qubits or 25 qubits, then things become a little bit more challenging to simulate. And there are, for quantum simulation, at least with analog and analog digital, there are no known, benchmarks telling you how good they are. Of course, when you talk about digital, then you have, your circuit fidelity or gate fidelity, and you could use those as benchmarks for telling you how good your simulation is. But in this case, it's very difficult for these problems. Now, if you're looking at some fermionic problems, for example, like chemical simulations or finding the ground state, then there are some acceptable thresholds based on quantum chemistry that you need to hit in order for your simulation to be accurate. But that's not the case for the work and the results that I discussed today, because they're not fermionic and they're not quantum chemistry, they're condensed matter simulations.
Okay, that sounds good. Then perhaps the last one from me would be, looking at where we are in Africa, how can people who are interested in doing quantum simulation get started? Given that they may not have access to the chip fabrication, to perhaps the lab, the equipment that is required to realize some of these experiments in physical terms, what would you say is the best way to get involved in this kind of work?
Yeah, so that's a really good question, because of course, again, I'm very fortunate, and the people who have done quantum simulation have been very fortunate to have access to labs that could have accommodated such experiments. And of course, building such labs is, first of all, not easy and also not cheap, which is definitely a barrier to entry. But again, something that I would like to encourage people is that, so again, in my work, I talked about analog simulation and analog digital quantum simulation. But you could focus on digital quantum simulation, and then that could be ran, or those areas could be explored on IBM quantum devices over the cloud. And I think that's a great resource that's available today. So again, that could be interesting in a sense that you could think about how you could simulate different physical systems using either gates that IBM has to offer, or the open pulse or the Qiskit pulse backend that they have available. And that is a problem that, to the best of my knowledge, at least as far as I know, has not been explored that much, because people haven't had access to these resources up until recently, up until this past year. So there's definitely something to work on and explore that should not require building a quantum lab of any sort from the ground up.
Sounds good. Perhaps as a follow-up on that one, what is the implication of Qiskit metal to work like this one?
Yeah, so actually we are exploring Qiskit metal in our lab to see how it works within the infrastructure that we have. So Qiskit metal falls, basically is focused on designing or providing the tools such that we're able to design these superconducting chips. And I guess where that falls is that in theory, again, we haven't tested it in our lab actually, but based on the demonstrations that I've seen, it allows you to really design and classically simulate the behavior of your superconducting chip before you fab it. Now we have different tools for that we're using in our lab right now, but Qiskit metal makes a lot of some of these tools widely available to the general public, which I think is very valuable.
So yeah, thank you very much, Amiri, for the presentation, and I think for the question and putting a lot of these things in context. Is there someone who wanted to come through? Okay. So anyway, thank you very much, everyone, for coming through. I think we have hit time. We normally have a cocktail, and I've shared the link. If you've got extra time, we'll be pleased to have you on the cocktail, and we can chat more about this work and about the other things that you're working on. And for people who are also part of this meeting, you can join the cocktail and you can chat to Amiri further if you've got time. I know that you're always pressed for time. There are a lot of meetings and other things to do, but we appreciate it if you can make it. I think this leads me to thank you, Amiri, for coming through and the presentation and everything else that we've managed to talk about. Thank you, everybody, for attending. And let's meet at the cocktail and have a great day wherever you are. Have a great evening. Have a great morning. And all the best with what you're working on.
And thank
I've
you so
shared
much
the
for
link.
having me.